very relevant one. The speaker today is Arnoldo Frigessi, who is a professor of statistics at the University of Oslo. He leads the Oslo Center for Biostatistics and Epidemiology, and he is the director of the SFI Big Insight. Big Insight, Center of Excellence for Research-Based Innovation with partners from industry, business, and public actors, as well as academia, developing model-based machine learning methodologies for big data. Originally from Italy, I've just learned that you've been here for 25 years, Arnoldo. Your Norwegian is excellent, but still this event will happen in Norwegian, no, sorry, in English. So please, Arnoldo, without further ado, take it away.
Thank you, Trym. Thank you very much for inviting me. It's a pleasure to be spiritually in Trondheim. It was in '94, I think, that I arrived in Trondheim for the first time in my life in Norway. I spent there 6 months. It was the winter and spring. Wonderful memories of the time. Håvard Rue, good friend, he had a pink bicycle that he didn't use, and that was my transport system in the snow, and it's very good memories, I have to say. But today I'm sitting in Oslo in the sun also, and I think that these COVID things has made lots of troubles, but also allows us to speak more often. And but I still look forward to see you in Trondheim sometime soon. So let's start. I should minimize this a bit. Yeah. So this is the statistical work that I've been doing together with Folkeinstituttet on the modeling of the Norwegian epidemics. And before I start, I should thank and present you to the Norwegian Institute of Public Health modeling team that has been working intensively for a year now. And here you see many faces and names, many from Folkehelsa, good friends from Telenor, Norsk Regnesentral are also here. And the project started really as a part of Big Insight, and now is really inside Folkehelseinstituttet 100%. In Norway, the government has decided approximately a year ago to keep control of the spread of the virus with interventions. And interventions have been both local and national. And in fact, local interventions are encouraged, and they start to be very visible now with special things in various places in Norway, though we expect some national interventions to be announced soon also. Controlling the spread really means two things. It's the most important one is to control the number of patients so that they are manageable for the health system. It includes the number of deaths, of course, but it's the hospitalizations that is crucial for the control. We remember and we see with horror what has happened in many countries in Europe, and this is what we try to avoid. And today we are again in a situation where, with the B117 variant, the UK variant, and others, we are afraid that the health system can come to a stress again. And the other thing that you want to control is the number of cases, essentially, because if the number of cases becomes too high, the contact tracing system might become inefficient or even fail. And this is very important because to identify cases by testing and find the contacts back in time and isolate them or put them in quarantine and test them, this is the way to break the chain of transmission. And if that contact tracing machinery fails, then the exponential growth wins. So these are the two things that have to be controlled. The modeling group received very clear tasks from the Folkehelse and from the government and connected to the strategy. which is to predict the number of COVID patients that go to the 20 hospitals in Norway, or how many there are roughly. Predict the number of patients requiring, in particularly invasive mechanical ventilation. Intensive care units are a scarce resource in every country, also in Norway. And I was hearing yesterday that Ahus, one of the big hospitals here in the region, has now filled up intensive care units, so had to move some patients to Oslo. And these things are really the important things. We also estimate prevalence and effective reproduction numbers. These are numbers that you all hear about. They are used, in fact, to understand where we are and to understand the risks that are connected to different type of strategies. One being continue as we're doing now, and the others being doing more or less in the future. And all these things have to be estimated and predicted both at national level for the whole Norway, somehow an average of the different type of populations and organizations that live in Norway, urban and rural and so on, and specific for fylker and for different regions. Important recently, another task that we received is to understand and optimize the national vaccination strategy. Predictions in the future are somehow of two types. One is very short predictions, 3-4 weeks, and the other one is longer prediction, 1 year, for example. And when we do longer predictions, they're really not predictions anymore. They are scenario simulations, assuming that a certain situation remains or is fixed. How will the future look? And the future situation can be fixed in terms of, let's say that we use the current reproduction numbers to predict the future, or we could make them a little bit higher if we think that they will increase, or a bit lower if we think that our interventions will be successful. And then we have to also put into the modeling of the future the vaccinations, because the vaccinations plan, at least, is defined, and we know when vaccines are coming to Norway and when they will be used. I'm not an expert in the vaccination part of our modeling group, so I will not be able to give much details on this, but I can point to others if there is interest in that. So the data that we have in Norway are the ones that you all know. And we have been using essentially 3 sources of data: the total number of tested and the positive number of tested. And here there's a big discussion, and you have to be careful in lots of small details. For example, if a person is positive and gets a positive test, he or she is usually tested again after a while, maybe even repeatedly, to see when the virus has left her body and she can go back to a normal life. So there are repeated tested on the same individuals. And here we have to be careful to distinguish those type of tests from the ones that are the first positive test that gives us an indication of when the person has been infected. Then we have information about the imported cases, imported into Norway, cases that come to Norway but as already infected because they have been infected in other countries. And because of this mechanism that they have not been infected in Norway, we have to treat them differently, because that positive case comes to the country and can infect others, but her infection has not been a product of the epidemics that we are modeling in Norway. We have also then the number, and that's one very important source of data, the number of patients that have been admitted to hospital because of their COVID-19 diagnosis. This is the new admitted per day. And there are other type of data, for example, the new admitted to ICU with or without ventilation, the total deaths and things like this that could be used. We don't use them for various reasons. And all this data are at municipality level, 356 municipality in Norway. Another very important source of data is the one that we have with Telenor. So Telenor Research has very important source of information for this model, which is the mobile phone mobility. So here you follow a SIM card, how it moves from one position to another. It's connecting to a tower, to which tower it is connected all the time. And this is a surrogate for real-time mobility patterns of individuals. The data that we receive every 6 hours from Telenor is a total count of mobilities between the 356 municipalities. So number of people that moved from Oslo to Bergen between 6 and 12 o'clock yesterday. It's a total count. And really it is even not so good as I told you. Now, it's not the total movements within the 6 hours, but it's the total movement only between the first 2 hours of those 6. So it's during these 2 hours that the location is monitored, and the last location recorded is the one where the SIM card was found at that point of the time. Counts below 20, so if only 10 people moved from one commune to another, are censored because of privacy. And these data are available from the beginning of the epidemics, and we scale up the Telenor market share to the national numbers. Mobility is, of course, changing very much, and I'll show you right away here a plot that we published yesterday. This is the number of SIM cards that move out from a commune every day since March until today, scaled up, as I mentioned. So here you see some curves. Maybe if you follow the red one here in the middle, you see the Norwegian average. So this is the total for Norway. So it was quite high in the beginning of March before the lockdown, dropped down when the 12th of March, where there was a lockdown, a big drop from 100. These are scaled values now, from 100 to 40, right? And then to 50, so halved. And then it slowly started to go up again. Here you see the summer. The summer, interesting things happen. Some cities lose people, and Tromsø got a lot. In the north, these are all northern fylker, because we had to take vacation in Norway, didn't we? So, and then it went down, and here you see, here's another lockdown, and then, you know, you might remember that the first week of December, schools opened again and went to yellow again. It was really a good time, and we see an incredible peak of movements in the first week of December, very unpredicted, at least for me. And what happened in that week? Everybody moved dramatically, and probably it was the start of the Christmas shopping, but also the need for all the shops and bedrifter to finalize the year, to buy the things that they needed to sell at the end of the year, and so on. So there's a big peak. And then you see that mobility has been more or less stable in the last period, at quite low level, right? We are quite at low level. Now, the light blue curve that is impossible to see is Trondheim. It's very much in the average here in the middle. This is the last days of the same plot, the largest municipality in each fylke, in fact. And here you see that this is the 4th of January when a serious set of intervention was set in place after the Christmas vacation. And usually, you know, when this intervention happens, for example, if you see back here, there's a big drop, and here the situation remained a bit essentially stable. So the movements have not reduced very much, a bit here, but it has been stable. Our regional meta-population model is using 3 sources of information. One, as I told you, the mobility is modeled by the Telenor data. Then we use the population structure from Statistics Norway that is frozen to January 2020. I think it's we should have frozen it again to 21. I don't think we have done it yet, but this is, we distribute the population into all the communes according to the demography that Statistics Norway has pictured. So in every community, we know the profile of age and so on. And then we have a compartment SEIR model, SEIR model, that is modeling the spread. And you have now seen these models in many forms. This is just one. And that's the one that we use, right? So everybody is susceptible. And if somebody gets in contact with an infectious people and get infected, then it enters a short phase when the person has been exposed to the virus, is not infectious and doesn't have any symptoms. And then there are two options. Some people continue to be asymptomatic until they recover, so they don't have any strong symptoms, or maybe not at all. And another group, maybe the majority, becomes symptomatic. And before they are symptomatic, there are a couple of days where they are so-called pre-symptomatic, which is a period when the person is highly infectious, but doesn't know about it. And this is where many of the infections are believed to happen, many. And then people are recovered here. So all these movements of people happen with a certain probability, right? Or happen with a certain strength. And it is this parameter beta that I will speak a little bit more about. That is a special parameter for every fylke. That's why we have an F there, and that changes in time because the transmission parameter is in its strength changes in time. So let's see the model. So here I show it to you. It's these models are quite simple. They are differential equation. In this case, it's stochastic differential equations to model a bit the model error that we introduced by simplifying the dynamics in this way. These equations cannot be solved analytically. You need some computers to do it and some numerics, but they're very simple, and there's nothing new here. We need to parameterize these equations. These equations are full of parameters, and so here you see some parameters. Here they are, right? PA and so on. So for example, we need to say how many people once exposed to the virus become asymptomatic and how many becomes symptomatic. And here we flip a coin with a probability 0.4 you are asymptomatic, and with a probability 0.6 you're not. This number comes from the literature. It's a number that is used in most models. It's not easy to estimate this number. It comes from the cruise boat that was studied very thoroughly a year ago. I can't remember the name of the cruise boat now. But this is a parameter, and this parameter we fix. We don't estimate it, we fix it. Then we also study, for example, how much time a person remains in this exposed group. And here we use an exponential distribution with 3 days. I'll come back to this number in a minute. Then you need to say for how long are you asymptomatic? 2 days, for example. And the rate of transmission is this beta t. So this is the probability of transmission upon contact. It is time the contact rates, and it's estimated. This is the quantity that we estimate. And once we estimate these betas, we can get the reproduction numbers. There's another very important parameter in our model. A very important assumption is this one here. So if a person is asymptomatic, how infectious is this person towards others? What is the probability that she will transmit the virus to another? And here we assume that this is only 10% of what happens when you are in an infectious compartment. So if you are in the infectious compartment, let's say that you have a probability beta t, and here it is 10% of that. And this 10% comes again from the literature. If you're pre-symptomatic, I mentioned this is more infectious, and this is 1.25 in our model. These are fixed. Once you have these betas, then you can compute the reproduction number R0 at time t. Here it is. It's an eigenvalue of some matrix. And what really matters is the so-called effective reproduction number, which is this reproduction number that you all know, that says something about how many a case will spread during the period he is infectious. But this is now estimated times the estimated median proportion of susceptibles at time t. So this is the effective reproduction number at time t. Now, as I mentioned, the dynamics, the model dynamics is controlled by the Telenor mobility matrix that we get every 6 hours. But we have to be more precise, because if we know that there are 100 people that move from Oslo to Trondheim during a certain 6 hours, okay, how do we choose them? Let's say that we choose them in some way. So we move these 100 people from Oslo to Trondheim. And now in the next 6 hours, there are 60 people that that apparently go from Trondheim to Oslo. So now the question is, who do we send back? Because Telenor doesn't follow people, we only get numbers. So we have to choose this 60, and we do it like this, that first we send back the residents of Oslo if they are sitting in Trondheim, and we need to send somebody from Trondheim to Oslo. We tend to send back the residents to Oslo. And this has to do with the fact that there is commuting, which is a very, very important aspect of mobility here, the most important. The second is that it can be that we have, let's say, 100 Oslo people in Trondheim, and we need to send back 150. So we need 50 more. And where do we choose these 50 more? Well, we don't have people from Trondheim, from Oslo there, so we have to take them somewhere else. And we take others that are visiting Trondheim, but are not from Trondheim. And the last one that we send are the ones from Trondheim. So this is how we decided to implement the mobility. Now, if I very briefly, I don't want to be technical at all, but I very briefly mention this important part that has to do with conservation of the population. So if xijt is the number of people who were in location I at the end of the 2 tracking hours of the interval t-1, and then are in location j at the end of the 2 tracking hours of interval t, then and xiit is the one that don't move, then this equation 1 that you write there has to be true because of the conservation of people, right? And if all movement would be recorded exactly, then the matrices that I get from Telenor would satisfy this equation, right? But they don't. And the reason is that there's more movements that escape the Telenor tracking. And this is because phones are not connected, or they exit the Telenor net, or there's other things like this. So this equation is not true. Therefore, we do not conserve exactly the population. And because we do not conserve, it can happen, in particularly for smaller municipalities that don't have much people, that suddenly we don't have any people at all there to send to where we should send them. The depletion can happen. Now, this is almost not happening if we do 3 weeks predictions. And if it happens, we simply add some people that we think are immigrating. But it is not okay for longer predictions. Then we need to do something more. We need to regularize these matrices so that they resemble the Telenor matrices as much as possible, but also preserve the population, conserve the population. And this, you can see, has to do with being the row sums equal to the column sums of these matrices. And therefore, we simply find the matrix Z that is closest to the Telenor matrix, but has this row sum, column sum property. And this we do with a quadratic programming program with linear constraints. That is easy. We do it before we do predictions. Then I have to tell you something about the hospitalization, because how do we send people to hospitals in our model? Now, here there is this famous time gap between when you are infected and when you go to hospital, if you go to hospital. The probabilities that we use, the fundamental probabilities of being hospitalized per age group, the first column, you see the age groups, 80 more here. So they come from a paper, a very important paper that has been updated a couple of times by Salje and others, This is a French study which is used by many models in the world. And we start with this probability that says, for example, that the mean probability to go to hospital if you are between 40 and 50 is 1.4, right? With a confidence interval here. Now, we have to adapt these numbers to the demography of each municipality, because in each municipality, we have different combinations. In some places, there are more elderly people, some places there are less elderly people. So we have to correct or scale these probabilities in each municipality differently, so that we send to hospital the population in each municipality with the correct probabilities. We know the demographic profile of each municipality, but our model doesn't have age structure. So when we move people around, we don't know what age they have. I can come back and say why we don't do this, but we don't have this. So we have to correct the probabilities to send the correct number of people to hospital. But there's another point, and this comes with the fact that the number of infected people is not following the demography. Here you see some curves that I think from the beginning of March until the end, until January, they tell you the proportion of positives in each age group. So the ones that you see here, the light green, is between 20 and 29. And this is an age group that was very infected compared to the others. During the summer, you remember when they were all partying and all the Trondheim students had fun. So here they are, but then they went back to understand the situation in here. And the elderly people here, the ones that came, let's see, the ones that came from the Alps in the skiing resorts, then they disappear. So this is very important. And we have this curve for every commune. Do I have them here? Yes, they're very different from various commune. And therefore we follow also this regional variation. We learn the distribution of the age of the infected from the positive tested. We compute a correction factor for each age group, right? And this is the ratio between the proportion tested for each age group divided by the demographic, and we make the corrections accordingly. And we do this only after 1st of May because we don't have so good data before that. If you put everything together, given symptoms, the risk of being hospitalized, if you are, is 2.3%. Then I have to say something about the time gap, as I mentioned before. And the time gap can be estimated from Norwegian registry data. This is data that are available and that follow individuals in their history through the health system. We have this type of data and we update these numbers approximately every second week. So for example, how much time takes it between onset of symptoms and hospitalization? And we found out that this is well estimated with a negative binomial that has mean 7.6 days. And if you are in hospital, what is the probability that you need intensive care units? This is 0.09. So it's a small probability. And here we want to know how much time people are in the ICU and so on, right? So all these probabilities are estimated and the distributions are fitted in some okay way every second week. We also have to say something about the testing and the probability of detecting a case. Because if we want to use, as we do, the test data, we have to, in our model, send people to testing when they are positive. And we do this by modeling a probability of detection of a positive case. And we simply assume that the number of detected positive cases is a binomial with an estimated daily incidence of symptomatic and asymptomatic. This is a number that we have in our model, times the probability pi t. And we use this is a time-dependent probability of detecting a case. And we model this by a logistic, in a logistic regression setting by assuming a constant intercept and then as a covariate, the number of tests actually performed on day T. So that's the dependence on time. The idea of using the number of tests actually performed on day T is because this helps us to quantify the effort that is made on that day to find the positives, right? Of course, this is not very exact, right? Because the effort that you do to find the positives is only in part described by the number of tests that you did, because the other thing is, where do you try to find them? I mean, are you testing in particularly in areas where the reproduction numbers are very high instead than others? Are you trying to test schools completely? And so because of this, the number is not per se fully informative, and introduces a little bias here. There's also a delay between the day of testing and the day of when the transmission really happened. And this is a delay that we estimate. The reason why we estimate is that it helps a bit to align the hospitalization data with the test data. For the, now I look to the time, yes, for the beta parameter, the probability of transmission, we use two different models. We use a change point model and we use a continuous time model and two different ways of doing inference. So for the change point models, we simply decide these parameters that change in time, they are constant over longer stretches of time. And we put the change points according to where the events of lockdowns or openings have happened. So currently, I think we are running these change points. That's how they are placed. We do at least a change point every month, but sometimes we do more. This is both at national level. These are the ones that we've been running this week, for example. After Christmas, we have a period from the 4th of January until the 21st of January, where we assume a constant reproduction number. And then from the 22nd of January to the 7th of February, that we have another constant, and then after the 8th of February. Currently, we run 8 with 14 reproduction numbers. Regionally, it's a bit different. So Oslo and Viken have more change points than the other fylker, because here we have a lot of parameters, and estimating all these parameters is heavy with our sequential ABC methodology, so that we try to have less parameters if possible and where possible. I should say something very briefly on the seeding. All the time we import cases from abroad, and here you see it's these darker numbers down here. There's also quite a big quantity of cases that are not known. They are afterwards, they are resolved, but we don't know it yet here on that day when I took this plot. And we think that these numbers here, the imported cases, these are the ones that we have recognized as imported, but everyone is in fact representing a small group of people. The other we haven't detected, they have escaped our system. And therefore we introduce a so-called amplification factor, which is an unknown factor, so that every person that is coming in fact represents, for example, 3 or 3.2 cases. We estimate that factor. So inference is quite complicated. We have a lot of parameters and several other factors, and we use the two types of data that I mentioned: daily new hospitalization, daily number of positive tests, and daily number of first tests made. And here are the data. So first of all, a comment on just to tell you about the difficulty of using these two sources of data. The problem is that there is a lack of coherence between test and hospital data. And this lack of coherence in many sources, but let me explain you in this little drawing what it is. Imagine that you have a test data here in this point here. And this means that, okay, the infection has happened a bit before. We have a distribution with a certain delay here. So this is where the infection happened, somewhere here in this period. And if the infection happened here, well, then we know that there's a certain probability and a certain delay that this person will produce hospital data, right? But if we start with the same hospital data and go the other way around, okay, here's a hospitalization case. This means that this guy has been infected here, and then it should produce a positive test here. So the two data sets are completely, in principle, are completely connected, but this is not the case because these distributions here are in fact changing in time, and we have no possibilities to adapt these changes to the data. We don't have enough data, so we have an incoherence that is there. Sequential Monte Carlo is a standard method. I maybe don't have time to tell you exactly what it is now. I will jump over it, but it's a method that is used to estimate the parameters, and it's a sequential method, an iterative method. So here you see one parameter that at round one of our sequential ABC, and we see how it converges. This is the posterior distribution of this parameter at round 33, for example. But for some, this is one fylke. Now I don't see exactly which one it is because I don't see the top of my figure. But this is Rogaland, and here you see that things are much more flatter. Look the difference between, I think this is either Oslo Viken, it has a posterior distribution between 0.9 and 1.3 and 1.4, for example. But if you go to Rogaland, look how uncertain things are. Trondelag also very uncertain. And this has to do with the fact that there is less information and less data in many counties because there's very little hospitalization in many fylker, and also less positive tests. And this is something we suffer from. Here you see the last estimates that we got for the national model. We are here now between 1 and 1.5. These are our estimates for the average reproduction number from the 8th of February. Here you see the new hospitalization. The red dots are the data. The shadowed blue things is our model estimates, and here you see the prediction, how we think it will continue in the next days. It can go up to 20, 30 new cases per day. This is a plot that shows the incidents that we estimated with our blue things. This is the number of people that are walking around every day with being infected, and the red one is the number of positive tests. And the difference between those two things is what is called mørketall. The positive we don't know about. There have been so far approximately 132,000 people infected in Norway, according to our estimate, up to 150,000. This is approximately coherent with the seroprevalence studies that have been made in Norway, which we haven't used. Here we study the probability of detecting a positive case. This is important because it says something on how good we are in detecting cases. We are around 60%, quite stable since after the summer. It was much worse before. This is when the test capacity in Norway has been increased dramatically. We are not at saturation anymore. Here there was saturation cases. The uncertainty estimated reproduction number for Viken and Oslo are good, small confidence intervals, credibility intervals. They're horrible for all the others, as you see. And this is a problem that we have currently with our regional model. We try to, as this is, I think, from this maybe 8th of February, we try to estimate recently the reproduction number, but when we do it too recently, we don't have enough data to really inform many fylke that don't have much information. So we have confidence intervals that are not useful for decision making currently. Here you see it very clearly. But the Viken and Oslo are fine. The uncertainty is, this uncertainty here is, there is a peak here, right? So it's, if you think to a Gaussian distribution here, for example, I mean, much of the probability is here, right? It's not up here. So we can still do predictions and simulations that are quite good. So here you see the prediction of the number of new cases for Oslo, for example, and the fit has been good so far. Then I would like to mention that we also have a model that has a daily reproduction number where it changes every day. So there is no change points, it changes every day. And this is based on a state space model and the sequential Monte Carlo inferential approach. I can give you more detail if you want, and we have I think we have a paper on archive on this, and the model is fitting well, and this is the current estimates of the reproduction numbers. So you see that now we are around 1.4, 1.5, maybe 1.4 here, like the other one. This is coming a bit closer, so we are only I think 1 week back from now. What is interesting is that you see, for example, the collapse of the reproduction number when there was a lockdown on the 12th of March, and then the oscillation during the summers. And you see here during the lockdown again at the end of November, it went down rapidly. During the vacation, pre-vacation, remember that peak that I showed you in the mobility, right? It created an increase in the reproduction number. Then there was Christmas vacation, it was fine. And then the new lockdown here. But here you see now we have essentially been in a very tough situation for a long time. Usually these are periods, here you see it and here you see it, when things go down, here they go up. And this is to do with the UK variant, right? That because of the infectiousness, infectivity of the UK variant, the B117 is maybe 50%, 30, 40, 60% stronger than the other variants, then the current interventions are not strong enough to keep the reproduction number down. And a reproduction number of 1.3 is too high. Then we would stress the health system very much, in fact. The drop of reproduction numbers is comparable in Norway to other countries, in fact. And I will now jump to a conclusion. I'd like to point to some challenges. First, what I mentioned is that using different sources of data is so important because they give so good information about different aspects. And we are happy to use test and hospital data, but we are aware that they disagree. And while they together give the best estimates of the reproduction numbers, if we want to make prediction of hospitalization, we probably should use only the hospital data. At least in some sense, weight them more. These are things that we haven't solved completely yet. We have not completely yet the issue of the convergence of the regional model. We're running the model on FRAM with 4,000 cores, and it's tough. And there is also an important time constraint. We get the data Monday morning, 10 o'clock, and then Tuesday evening we need results because they are published on Wednesday at 12 o'clock. So this is our window where we have to run things and get results. And it's tough because we have lots of parameters. So we have been working on methodologies that are freezing, in some sense, older part of the history and estimates. You can think, why do you need to estimate the R in August so precisely in Trøndelag? Who cares about that? Well, it has an effect until today, in particularly the uncertainties. So we have a method where we froze the past, but we keep the uncertainties alive so that we don't underestimate it too much, at least. Uncertainty propagation is important, and we don't propagate it properly. There are many parameters that are fixed in the model without any sensitivity analysis. For example, that 0.4 that I mentioned for the probability of being asymptomatic. There are also, but many parameters, even if we estimate them outside, for example, the hospitalization parameters, their uncertainty in the estimate, the negative binomial, that's taken into account because we sample from those distribution all the time. And then we have these challenges with the multiple variants, the UK variant and others. And here, it's not difficult to make models that have also that type of compartments, but you need data quite specific data to estimate, for example, a reproduction number for the UK variant, which should be higher than the one for the other variants. And we are working on this, and it comes very soon. I will stop here because we need some discussion, and I will not tell you all this other part here. I can come back to this, but I think I have a one sentence conclusion saying that this is one of the many good models. There are very many other useful and good models. Inference is difficult. In fact, it's few data. The epidemiological system is complex and has lots of parameters, and the model is available through simulation, which is time demanding, right? Mobility is important. It's in particular important when the epidemics is at start and when it restarts after every intervention. The regional scale is useful, but the quality of our estimates is not the same in every part of the country, and uncertainty is really informative, even if it is big. And so we should continue to show it. Thank you very much. And I'm sorry if I spoke too much.
You didn't, Donald.
It's fine. Okay.
That's perfect. I think it's perfect. We have and we have 12 minutes for questions. So I'll ask you to ask your questions in the Q&A, or you could also raise your hand. So let's try some of the questions from the chat first. I have one here from Ingelin Steinsland.
Ingelin, yes, hyggelig å
And it
treffe
says,
alle gode venner.
And I'll read it out. Starting by thanking you for a nice talk and your important contributions and effort last year. 2 questions, actually. 1, which of your assumptions do you think are most critical? And the second one is, what have you learned about knowledge gaps and other challenges during the last year? Anything we should consider for our teaching or studies or research?
Many good points. So what is most critical? Some things are more critical than others, right? I can say that, for example, the hospitalization probabilities that we're using are very critical, because if we get them wrong, we will make very wrong estimates of the probabilities of the hospitalizations, and that is something that we have very good data about, and so it's critical, but we can do something with that. Then there are parameters that are critical that we don't know anything about, and for example, the 0.1 of the infectivity of the asymptomatic cases. That is an important parameter, and we have no way of describing the uncertainty around it and play with it. Now, having said this, in the practical decision making that happens in Norway, the differences from one week to the other are important. So freezing some parameters to a value which we are not sure if it is true, but still this allows us to follow in time reproduction numbers. That is important in any case. So they might be wrong, right? It might be 1.4 instead of 1.3, but does it, if it doubles, it doubles, right? And so that's one thing. The other question was about knowledge gap, right? So well, this is broad, right? So first of all, we know very little about COVID, and we have been changing our model all the time, and we change it all the time still. We have 8 pages of changes on the web. We make mistakes. We have to correct mistakes. We make wrong assumptions that have to be corrected. We understand that a certain assumption needs to be put in. And Ferguson and Fraser in the UK are correcting their models all the time. So I like to think this modeling science as something very new. I call it evidence making, in the sense that we are it's not like usual that you have all your knowledge, all your data, you make the solution. This is my prediction. Let's see if I'm right tomorrow. I will be. It's changing all the time. I'll stop here, Trim. Otherwise, we
Very
could
good.
discuss
Thanks.
also what it means for teaching statistics and so on. That's interesting.
Let's try to bring. So Bernd, you have raised your hand. Marianne, can we open the microphone for Bernd? Bernd Schmid, you can ask your questions live. Question live if you want to.
Hello. Yes, do you hear me?
Yes.
Okay, sorry, the meeting was on both sides. Okay, I was just wondering about, there has been this discussion in the public lately about curfew and portförbuds. So what would be the effect? I recognize that maybe, so you have been modeling on traveling, or you have this data inside from Telenor, but is it possible, or have you been looking at it, what the effect would be on the reproduction rate, and would there be regional differences expected?
Yeah, so we have done scenario simulations where we introduce different type of things, right? So for example, we can stop mobility in the future and see what happens and things like this. We can do this. It has not been very interesting in some sense because the future is so unstable, right? And that it's a bit difficult to say something about the long-term future where we know lots of things will happen, right? So we haven't done it very much. We have done lots of scenario simulations now on the vaccine thing, right? For example, and in the past we have done also some counterfactual thing, but we have not done much. But if you ask me what would happen if we would stop all mobility, you know, mobility between communes, that would have an effect in terms of allowing certain areas that are free of the virus to remain free. Inside Oslo and inside Trondheim, we are assuming a complete mixing in this model. So that will continue. If you want to stop also that, we have to make assumptions on the betas, right? We can do it, and we will, in some senses, what you put in the model, it comes out. So we will not find surprises here. Yes, it will reduce the reproduction number, and it will reduce as much as you want, according to how you screw the parameters, right? So it will be very difficult to do anything interesting, in fact. But it would be nice to do it, but I don't think we can.
Okay, thank you.
Thanks, Arnoldo, and thanks, Bernd. We have one more question here for you, Arnoldo, regarding the model. So it's from Shamini Alagaratanam. Sorry about the pronunciation. And it's a question about the model being, is it a quite a standard one for COVID transmissions, and how does it compare to models used in other countries?
Yeah, it's these models are slightly different all the time, right? But they are all in the same family. So some difference in the compartments, but in some sense it's in the same family. So it's nothing revolutionary. It's quite unique that we use regional data and that we have the mobility of Telenor. I think there are maybe no regional models around. Norway has also quite a, I mean, Denmark is much more compact in some sense. They don't need regional models in Denmark, right? Italy has regional models, for example, but they are separate. Different parts are separate. We have a regional model that is connected, fully connected. So that's a difference. But you are very right that these compartment models are very classical, and there's no magic there. And I mean, there are details, right? How we introduce the test data by assuming that every case can be detected with a certain probability is slightly different than it's done in other places, but it's not very high tech. What is really high tech is to estimate 100 parameters with sequential ABC. That's difficult, and the way we do it is I think okay, but many have said that this is tough. It is tough.
We have one question here on sort of the technical level from Christian Brudli. He's asking which programming languages and tools are used for the implementation and simulation.
This is C++ and R.
So pretty straightforward in that.
Lots of parallelizations. All the simulations are parallelized. It's running on many cores. And the implementation is made careful so that we can try to be a bit efficient.
Mm-hmm.
But you can always be more efficient, of course.
Very good. I think our time is running towards the end here. So thanks again for a very interesting talk, a very, very relevant talk, I think. Very important work. Thanks to everyone who joined this webinar. Thanks for those of you who participated, asked questions, interacted, and thanks Arnoldo. And I hope to see all of you back for our next webinars the coming weeks as well. So thank you very everyone.
Much. Thank you very much for inviting me and for listening to me. It was a pleasure.
Thanks, Arnoldo.